the topic of my talk today is really, it's based on about 10 or 12 years of research that I've been working on. And so my title is Energy Made Visible, a Geospatial Implementation for Millions of Homes. And before we go any further, I just want to sort of draw your attention to this image on the left-hand side. It's actually a plan view remote sensing image from an airborne sensor. So it's taken from an aircraft looking down at the ground. Excuse me. This is a very, very large commercial building. The image has been resized so that it fits a very small window. But the camera that we use is a high resolution thermal camera. So it's a camera that senses thermal radiation. And what we're able to do is we're able to convert that signal, which is a grayscale signal, and convert it actually to temperature values. And what we've done here is we've made it so that red is hot and blue is cool. And so you can see in this image where the energy is actually leaving the rooftop of this building. And the small circles that you see there on the left-hand side, numbered from 1 to 10. Taylor, can you guys see my mouse?
Yes.
Yes, okay, so number 1 is here, because if I were to say to you, where was the hottest location on this rooftop, it would be very hard to figure it out, but we can define it. Here's the hottest location first, second, third, fourth, all the way up to the 10th hottest location. And there's actually a very important scaling component in this, because you don't want to have all of your hotspots in one location, but how far apart should you actually have your hotspots? And when you take your data set, that could be, in this case, it's a very small window, it's about 512 by 512 pixels. This is a very, very large building. So when you resample your data, you're also changing the spatial resolution of it. You're changing the digital numbers as well. So I just want to sort of bring your attention to, this is a part of the kind of product that we actually develop using high resolution thermal imaging. You're going to see a lot of different images throughout the presentation. And the logo at the top is a triangle, and the triangle is actually the elemental symbol for fire. So this is the symbol that we use in a startup company called MyHeat, and I'm going to tell you the story about that. So let's see how we can make this work here. So what are we going to talk about? First, we're going to give you a very quick primer on what is heat. And then going to talk about how the project really began in the very beginning, urban energy challenges, the research that we developed at the University of Calgary called Heat Energy Assessment Technologies. And then I'm going to describe to you the different kinds of things that we do. So it's very much a remote sensing, geospatial, GIS pipeline. And then the different products that we develop, and then some examples from a utility company that we're working with, and then some of the really interesting research and development that's going on in my research lab and at the University of Calgary. So what is heat? I think I'm going to stop the video here. I'm just talking to myself. Can you still see the text, guys?
Yep, good to go.
Yep, okay. So everything above absolute zero, or minus 273.1 degrees Celsius, emits radiation, and it emits it in the infrared range of the electromagnetic spectrum. Okay, this is important to recognize. Now, any object that is hot, so it's moving, gives off energy. By moving, I mean anything that is at absolute zero there is no motion there. Molecules, atoms, things are not moving as far as we're aware. As soon as you get above absolute zero, you start to have movement of molecular structure. And that movement gives off energy, and that energy is known as thermal radiation. So the hotter an object is, the more thermal radiation it emits. So this image on the left-hand side, I wish I could have a classroom here and we could talk about it more, but I would ask you, what do you think this is? And the correct answer is actually an ice cube in a glass. And as you can see on the right-hand side in degrees Fahrenheit, there are different temperatures that have been colorized. And so this is a ice cube at the bottom of a glass. So we can look at things that have very small or relatively fine spatial resolution. But then if I was to ask you, what is this? And this is also a heat image. Could you tell me what this is? And this is 130 million light years across. This is our Milky Way galaxy. And in this image, the white areas are the hottest, the black is the coolest. And so everything that is moving, everything that we're aware of in the universe above absolute zero, is giving off electromagnetic energy that is referred to as thermal radiation. A portion of it is thermal radiation. And this is the kind of stuff that I'm interested in. So this is your thermal primer. Now you know that hot things give off more thermal energy. And we have a lot of different camera tools and technologies that allow us to be able to define those. So one day, it was about 2006, 2007, I was at my house. It was a new house at that time. And I came home And my home was super energy efficient. I built it this way. It was very highly insulated, triple pane windows. I even had the whole thing hooked up to all the circuits so I could see the energy that was being used. I had a wind generator, solar generator outside. I was pretty much an energy geek. And I came home one day and my house was cold. And I thought, why is my house cold? Wouldn't it be great if I could click on Google Maps or click on my iPhone and up would come an image in Google Maps showing me the energy that was leaving my home? But it wouldn't be an image that we would normally see like the one you see on the left-hand side there. Instead, it would be color-coded from red to blue. Red would be hot, blue would be cool. And it would have some little circles on it. These circles would show me the hottest locations in my home. And then I could interact with these circles. So I could say that at this location, there are windows or doors, or the system would ask me, are there windows or doors here? And it would then send me off to different retailers who could sell me or could fix my problems if I had a lot of energy that was being released at this location. And then we could even do this over time. So we could evaluate that once my home, all these red areas are removed, and they're now the energy efficiency in these portions is improved, I'm not wasting so much heat anymore, I could actually evaluate over time to see how well it's working, and as a measure of how well the service provider provided the products. And I thought, wow, this would be so amazing. And what if we could do this and make it free? And what if we could do this and make it free for millions and millions of homes? And to be truthful, there was people talk about having aha moments. Well, that was an aha moment that happened in a fraction of a second that has taken about 15 years or 16 years to materialize. But we're slowly doing it. To understand how to do it, I needed to do some research. And the research was, well, is anyone else interested in their home losing energy? Are we losing a lot of energy as a society? And I began to realize that the world wastes more energy than it uses every year. Think about that for a moment. The world wastes more energy than it uses. It's like having a wallet full of money and you get your paycheck and throwing out half of it, just letting it burn. It's crazy what we're doing with the energy that we have. The United States alone wastes about 70,000 petajoules per year. And when I read that, I thought, what's a petajoule? An equivalent of a petajoule per day would be about $384 million wasted per day if natural gas was at $2 a gigajoule, which is a very low price. So there's a tremendous amount of energy that's being wasted in the United States, but it's not just the United States. Worldwide, buildings consume about 40% of all the created energy resources while wasting in excess of 50% of the energy used. This image on the left-hand side was taken by me one wintry morning at minus 31 degrees Celsius. And I realized as I looked at the city that I could see that wasted heat leaving all the homes. What you don't see in this picture is that the whole city looked like it was made of smog. And that was all the wasted energy that was just around all the buildings. This is happening every single day. But because we can't see it, nobody does anything really about it. Over the last 5 years, the urban energy demand in Canada has risen nearly 20%. So we're wasting a lot of energy. We're consuming a lot of energy. Energy demand has increased, and yet we're wasting so much. On average, buildings in Canada emit about 30% of all greenhouse gases, 10% of all the airborne particulate matter. In Canada, we use 33% of Canada's total energy production and consume 50% of all natural resources. And what do we do with all of that energy? Most of it is used for space and water heating. Space and water heating. There's got to be a way to be more efficient. In fact, energy efficiency is the cheapest and most environmentally friendly source of energy. Energy efficiency is is less expensive than solar, than wind, than hydrogen. It is the least expensive form of energy. So how can we harness this kind of energy? How can we harness it to be more energy efficient? Well, the problem with energy efficiency, in fact, the most cited obstacle to energy efficiency improvements is a lack of interest. People don't really care about energy efficiency. Can you think why? Well, it's pretty easy. It's difficult to be engaged in something you can't see. So I'll ask you this question. What does energy efficiency look like? When people talk about energy efficiency, they talk about often reducing the amount of carbon dioxide and other greenhouse gases. What are these invisible greenhouse gases look like? We've been shown that meaningful feedback enhances energy efficiency and significantly reduces energy consumption and greenhouse gas emissions. This was a system that was set up in my house in my old home. Had it set up to something like 12 different circuits. And I could see how much energy was being used in my basement, how much was being used in my bedroom, how much was being used in all sorts of different places. So meaningful feedback is very, very useful. But the question becomes, what is meaningful? Is this meaningful to you? After a while, it became extremely boring because it really wasn't changing that much. Now, it just so happens that what is meaningful is really very interesting. We think that things that are meaningful based on what it is that we think are important. But it just so happens that when you start to look into social norms and the behavioral sciences, individuals are motivated much more by their perceptions of what other people do and find acceptable than they are by other factors such as opportunities to save money or conserve resources, contrary to even their own perceptions of motivation. So if you, in a simple world, if you were to say, you know, what's the most important thing about energy efficiency for you? And people would say, well, it's saving money, or it's you know, being good for the environment, or it's conserving resources. Actually, it's not. Those may be things that they think are important, and in their heart, maybe that's true. But when the examinations are done and when the surveys are done, what's really important is what other people think about what other people are doing. How other people think about whether or not you're energy efficient, about whether you're an energy hog. So as I started to look at the information in social behavior, as I began to look at the information on energy efficiency, as I began to look at the information on how can we even detect energy coming from buildings, I started to have a series of questions that I needed to ask. So my early science questions were very simple. I'm a geographer. I'm happy to be a geographer. So my first questions were related to time and place and space. Well, what does energy efficiency look like? Where is energy efficiency located? Think about that for a minute. Where is your energy efficiency located? And in fact, I haven't even said what energy efficiency is. And all of you are nodding your head, and you have in your mind probably an idea about what energy efficiency is. And there are many, many different versions of what energy efficiency is. But in simple terms, energy efficiency is doing the same work with less energy, or providing the same services or products with less energy, or the same amount of energy. So where is energy efficiency located? How can a homeowner know if their home is energy efficient? How can a municipality, a large city, communities, know that their communities are energy efficient? Gesundheit. How can we engage people's perceptions to motivate them towards energy efficient behavior? How can we use these ideas of perception to motivate them to do something? So these ideas started off about 2008, 2009, and we developed what we called the Heat Energy Assessment Technologies Research Program. So it was the HEAT program. And since then, we've been doing research for about 10 years. We've done a whole bunch of different things. We've been awarded pretty good funding, about $1.6 million in funding. We've created 10 pieces of intellectual property. I've been involved in the training of 22 highly qualified individuals, graduate students, PhDs, and postdocs. We were able to give a lot of media conferences, written at least 10 publications, there's more. 90 plus conference presentations have been given. I've got one patent, and one patent is pending. But most importantly, throughout all of this, as we started to develop these ideas and try to understand what was happening, was this program that we won in 2013. So MIT had a climate prize. It was called the Climate Collab. It's still running today. And in 2013, in November, we beat out 400 contestants worldwide for our pilot project, which had about 27,000 houses online that people could evaluate the energy leaving those individual homes. And from this, we did over 35 media presentations, provincially, nationally, internationally. In 10 days, our website, we had a pretty good website set up. We had everything set up so that if a lot of people did come in, we'd be good. We received over 40,000 visits, 110,000 page views. But most importantly, this was from over 1,000 different cities throughout the globe in 97 countries, speaking 38 different languages. So this really helped me to understand that energy efficiency and the problems related to energy efficiency, the challenges and the opportunities related to energy efficiency, are not just in my backyard, not just in my home, but indeed are worldwide. And it was interesting to note that there were 6 core sectors of individuals that were looking at us. That were coming to visit us in our project. It was the energy sector, banks and investment, the residential construction, real estate, information technologies, and government and municipalities. And from this win, we actually had the city of Paris and Washington, D.C. phone us up and say, hey, we'd really like you to do your heat project. We'd like you to do it in our cities. And at that time, we had, like I think it was about 29,000 houses online in a city that has over 450,000 houses. And it was web enabled and would allow you to be able to have access to individual houses and see the energy leaving individual houses. But there was no way that we could do that. We'd spent 5 or 6 years putting this together, doing a lot of testing, acquiring the data sets, getting permission to do all sorts of things. So in April 2014, we built a university startup and we called it MyHeat. So this is essentially the mantra for MyHeat: energy made visible, helping millions visualize home heat loss. So if you look at these buildings, this is what a regular high resolution color image looks like. Red, green, blue image looks like. You can see the individual rooftops. But this is what happens when we use our technology. You can see red is hot, blue is cool. And if you look carefully, you can begin to see, particularly in places, so here are the garages. Most of these houses have a front garage. This is a cool garage. This one is a hot garage. This one over here is a hot garage. This one here is a partially hot garage, a hot garage, a hot garage, a hot garage. Where do people typically have windows? They have them in the back of their home. And in this case, this home is looking over a lake. Windows have a lower energy resistance, an R score, than the size of your building. So energy tends to leak out through your windows and your doors before it leaks out through your walls and your ceiling. So what's interesting here is that every single building has a thermal pattern of heat loss. And every pattern is different. And yet there are a lot of similarities between each of these patterns. So this was done for 15 buildings, but we've been able to do this for millions of buildings. But in the beginning, we did it for 27,000 buildings. So our goal is energy made visible. And the reason for that is if we could show you where your energy is leaving and we could tell you what to do about it, I think a lot of people would be willing to do it, particularly if they could get money for free to help fix their own home. In fact, that's a real thing. People are giving away money for you to fix your own home. And I'm going to talk about that a little bit later. So our mission is to empower a worldwide reduction in urban waste heat and greenhouse gas emissions, one building at a time. I say one building at a time because we process everything as an individual building. But we look at thousands and hundreds and thousands and even millions of buildings. And when we provide city data sets, if your city has 30,000 houses, you get 30,000 buildings at a single time. Our mission is to define urban energy efficiency from space by visualizing the waste heat escaping from homes, communities, and cities, and providing a platform to engage, educate, and encourage action and accountability. It's difficult to do something about anything if you can't measure it. Once you're able to measure it, then you can monitor it over time, and then you can start to do something about it. Our goal is to make the heat that is leaving millions and millions of buildings visible so that people can see it and that we can quantify it. Now, to be able to do this, we do a lot of different things. So I'm going to break these down into our pre-processing and our post-processing. And remember, this is 22 different individuals have been working on this. There are PhD theses built on these. So some of these are just 1 or 2 slides, but it gives you an idea about some of the kind of geomatics technology and tools that we're using. So we're going to briefly talk about the data collection itself. Because we fly from an aircraft, we don't have one large image of a city typically. We have multiple flight lines that need to be mosaicked together. We have to do data normalization because as the aircraft flies back and forth, the temperature is changing. The wind is blowing. The aircraft is moving. The world around us is changing. As the wind is blowing, the temperature is changing. Microclimatic variability, evaporation occurring, transpiration occurring. All these different things are occurring as the aircraft is acquiring data. So we developed some technologies there I'm going to talk about. And then I'm going to talk about some of the post-processing that we do about the building extraction and the MyHeat products themselves. What's important to realize in all of this is that my work in this program came out of scale and recognizing that as you change scale, you change your vision, you change your perception of the world around you. And we know about the modifiable aerial unit problem, but it just so happens that Dr. Fotheringham also suggested a long time ago that objects represent a way out of the modifiable aerial unit problem. So we use individual house objects as our way to be able to evaluate our products or evaluate the landscape through time and space. So I'm going to talk about how we do that. So on the left is a map of the city of Calgary. Calgary is in Alberta, Canada. It's on the about 90 kilometers away from the Rocky Mountains. It's a large city, very large city. Area-wise, it's about 825 square kilometers. It's in the top 15 or 20 large cities worldwide. We have a lot of space there. The sensor we use is called a TABI 1800, and this stands for Thermal Airborne Broadband Imager. It's a broadband imager. We only collect a single channel of data between the spectral region of 3.5 and 4.8 micrometers. Satellites typically collect from about 11 to 14, 11 to 16 micrometers. We collect through 3.7 to 4.8 because it has better haze and smoke penetration. And this is increasingly used by folks that are working with fires. The sensor is 1800 pixels wide. So we can collect 1800 pixels, and we typically collect it between 25 to 50 centimeters. Now the thermal resolution of the sensor, it's a cryogenically cooled sensor. It's impressive. We can collect data at 5/100th of 1 degree. So 0.05 of 1 degree. Okay, so we have a very fine thermal resolution. We can collect about 120 kilometers at a 0.5 spatial resolution. But to collect the city of Calgary, you can see in the red there, that's one flight line. We have to collect 48 different flight lines, and they have to have an overlap so we can geometrically correct them to each other. Now to do this, we only collect in the nighttime. During the daytime, the house and the world is heated up by the solar energy. So it's very difficult to distinguish the energy that's going to be leaving your building versus the energy that is being heated up by the sun, or that is based on where the sun has been heating you up. So our acquisitions are at night between about 8 p.m. and about 4 o'clock in the morning. There has to be a low wind speed so the platform is stable. There can be no standing water or snow or ice for a minimum of 24 hours in advance because these are thermal insulators. And we record air temperatures before and after one day just to be able to see how the environment is changing over time and space. And what's interesting is that there are also air temperature recordings all over cities that are put up by volunteers. And so we have access to these through a Weather Underground program. On your left-hand side is an image, bottom left is an image showing what the thermal data sets look like that we collect. This is a larger sample of that. Excuse me a second, I'm just gonna have a drink. It's beautiful imagery. What you can see in the bright colors are the hot areas or the warmer areas. Black is cool, so you can actually see on the left-hand side there above the building, the structure of the individual tree branches. You can see individual trees. If you look to the right-hand side, you can see the buildings themselves, the rectangular shapes. You can see cars in parking lots or outside vehicles, outside the streets. You can see the streets. But as you can see, the roads are warmer than the buildings, than the rooftops. So we need to be able to isolate individual rooftops. We can't apply a measure over the entire image and expect it to work perfectly for each one. So again, we work individually on individual buildings. And then we take this gray level image and we colorize it based on the digital numbers which we get. So one of the things we need to do is we need to create mosaics. Now, we created a tool called object-based mosaicing. You'll hear me talking more and more about objects because objects we realize are a way out of the modifiable aerial unit problem, but objects are really what's important to each of us as individuals. We care about the things around us, and they're not usually just perceptions, they actually have a physicality to them. Now, if you understand what happens in remote sensing when you have flight lines, imagine you've got 2 pairs of socks and you're hanging them up beside each other. The idea is to make one big pair of socks instead of 2 pairs of socks. And if you had 30 pairs of socks, the idea would be to make one giant piece of cloth instead of having multiple socks. So we take our individual flight lines, remember in this case for the city of Calgary, we had 48 of these, and we need to mosaic them, we need to join them together. They usually have about a 15 to 20% overlap, so we can see one portion of a house in one building, in one image, and then the adjacent image, we can see the same house, so we can automatically mosaic them. Now, what we do is, before we mosaic them, we actually put a buffer around every single GIS polygon. So we've got rooftop polygons that have already been created. we put a buffer around them that is, we consider this as just going to be the error, potential spatial error. Now, typically what would happen when you would mosaic them, you would just cut them straight down the center or along the edge of your, right along the edge of your flight line, and then just join the flight lines together, or where the overlap is. But there's a problem with this. When you do this, you cut portions of houses in half, which means that you get temperature from one flight line, and then it takes 15 minutes to get temperature from the other flight line, and the microclimatic variability, the wind, the atmosphere, all of these different things will have changed. And so the temperature for that other part of your house is no longer the same as it was on the first side of the house. And in fact, when we do it for our City of Calgary data set, where we have over 400,000 houses, when we automatically make a mosaic, it cuts through over 14,000 individual houses. And I'm going to show you why this is important. So what we do is we mosaic around our houses. We automatically mosaic around the houses. We don't have to create this individually. We do this automatically now. So we're using objects again. And this is why it's important. This is the same house. Looking at the top with a traditional mosaic, you can see at this line here, there's a warp. That warp is where the two images have been put together. But if you look at the image below is taken from the same flight line, but we're mosaicing around the house rather than bisecting the house. And this is very important because if you look at the top image, on the top right side of that building, it's very bright up in this area up in here. It's very bright, but it's not very bright in here. So if we're going to define what is the energy mass or the energy amount leaving this home, we want to make sure that it's taken from a single instant in time, not over multiple dates. So we would then take it from here. And this is really important, particularly if we want to be able to evaluate the hottest locations in the home. So we created object-based mosaicing, and it turns out that our tool is 60% faster than traditional mosaicing. Let's see. The next thing we needed to do, we needed to be able to, it's referred to as normalization, make it so that it appears that the different flight lines that are mosaic together were acquired at the same time. So on the top left, you can see that this is the original image, and at this location, the two flight lines have been put together, just like we showed. But we developed a technology called relative radiometric normalization, and we compared it with 3 other leading edge normalization algorithms. And as you can see, there's still lines in each of these different ones, but here the line is essentially gone, and it's done automatic. And what this does is it mitigates for the differences in thermal energy and the overlap between the flight lines. So we collect individual flight lines, we mosaic them together, but at that overlap, we need to make it as if it was looking like it was collected at a single moment in time. So we get rid of the overlap or the normalization between the flight lines. The next thing we need to do is we need to be able to figure out how to normalize the variability within the flight line. Why do we have to do this? Well, the flight line is not an instant in time. It's collected over time. It's collected from the beginning of the city to the end of the city, and then we turn around and we fly back again. So each flight line takes about 15 minutes. And during that time, there is wind blowing in the city at all times. And so we need to be able to normalize for those differences in wind. So the idea here, it was a really great idea. The idea here is that large masses don't change a lot over time, given differences in temperature. For instance, the road is very, very heavy. It's made of a very dense material. And at nighttime, the temperature of the road almost never changes, or changes very, very, very little. So if we could find all of the roads in the city, and we could have an assessment of what their mean temperature is, or their average temperature, their most frequent temperature, then what we could say is, when we fly our aircraft over it, assuming that all the roads are made of the same materials, the difference we see in our image is not based on the road itself, but it's based on the atmosphere, the microclimatic variability, and the wind between the ground and the sensor. Does that make sense? If the aircraft is flying and it's at 1,000 meters, 4,000 feet essentially, and the wind is blowing and the aircraft is flying back and forth, back and forth, back and forth, and even if the wind is just 5 or 10 kilometers an hour, that's pretty low, but it's still moving. The world is still functioning even late at night. So there's all sorts of things going on microclimatically speaking. And when I say microclimate, I mean within 5 to 10 meters around your own home, everywhere over the city within 5 to 10 meters. In this image on the left-hand side, we can see that there's a lake up here on the top left. There's green space over here. And so our goal is to be able to try to figure out what is happening during the 15 minutes that the aircraft is acquiring data. How can we get rid of the variability that is not related to the actual homes themselves with energy leaving? Instead, it's based on the environment itself. So this was a really very interesting project. It was one of the first in the world that we're aware of that actually reduces the microclimatic variability. And the reason we do this is because this allows us to collect under very different environmental conditions and on different dates. This will allow us to normalize to a common road temperature. So all of the data sets that we use can be evaluated together. Otherwise, every data set is unable to be evaluated together. And so what we did is we sampled the roads at 5 meters, 10, 50, or 5, 10, 20, 50, and 100 meters. And then we interpolated the temperatures between these roads. And as you can see, where there are roads, there tend to be buildings. And so we're able to interpolate the change in temperature over the buildings that lies or exists between the different roads. This is a really useful tool that we were able to develop that allows us to normalize the data sets. Now, once we've normalized the data sets, we need to actually fit our houses, our polygons of our houses. We need to look at the individual houses. So what we've been doing is that we've been taking a polygon and overlaying it, geometrically overlaying it right on top of the building. And then we extract the information, the individual pixels that record the temperature underneath that polygon or within the boundaries of that polygon. But what we realized is that there were problems. The polygons that we were getting were either free and open source, and we're talking about hundreds of thousands to millions of polygons now. They were free and open source, or they were provided by the city, but the city didn't acquire them from a thermal sensor. It acquired them from usually a high resolution red, green, blue true color sensor. And so the polygons, while they fit pretty well because we've geometrically corrected them and we've got 25 to 50 centimeter data, they didn't fit perfectly, which meant when we put a polygon on top of your rooftop and we wanted to know how hot your roof was, if that polygon was actually partially on the side of your house and in the neighbor's property, it would give a very different value and it would show different hotspot locations than if it was really on your own roof. So we developed a technology called object-based geometric fitting. We received a patent for this on May 31st, 2018. So it's a really useful thing. So we'll have a look at this, how it works. So on the left-hand side, you have the color image. On the right-hand side, you have the thermal infrared image for the same scene. On the bottom here in number C, you have in red the polygons that are created off the RGB image. When we overlay them on the thermal image, they look pretty good until you get close to them. So our technology takes them and individually fits the polygons. And so you can see in this larger image here, the red was the original polygons from the RGB image or the color image, and the blue represent the fitted polygons. Now you might say, well, why don't you just move the polygons up 2 pixels to the top of the screen and then 3 pixels to the left? The problem is that every single polygon needs to be shifted differently. And how do we know this? Well, we did a little experiment. We took 29,000 polygons and we shifted the polygons between 1 and 4 pixels in the 8 cardinal directions, with 0 being no shift. So we had 29,000 polygons, right? We used object-based fitting to make sure that they visually fit, and it's based on specific secret sauce that we've created. This image on the left-hand side shows you the 8 cardinal directions, the number of polygons that were fit. Only 9% of the original polygons were at 0, which means that only 9% of the original polygons we received from the city data set fit our thermal data without being moved. Some of them needed to be moved in north, and then to direction 2, direction 3, direction 4, 5, 6, 7, and 8. And how far did they have to be moved? About 9% of them were perfect just where they were. Well, it's the same number essentially. 33% of them needed to be moved at least 1 pixel. 39, almost 40% needed to be moved 2, and then we get down to 3, 4, 5, and more pixels. So if we go back to this image here, you can see that each of these individual houses is moved individually. And now our polygons fit the houses. We have to assume that the polygons are high quality. That's not always the case, and that's some of the work we're working on now. But in general, it's very good. So now we have a tool set that allows us to take our thermal image, acquire it over in a very large city, like 825 square kilometers, normalize the data set so it appears as if all the images were collected at the same time. The imagery have been corrected for atmosphere and for wind and for other things. So what we truly get is temperature of buildings. The energy that is emitted from a building. It's not reflected energy. Thermal radiation is not reflected, it's emitted from structures. So we're looking at these grayscale images now, and now we can look at the individual objects themselves because the polygons that we have created now fit them very well. So this is really, really important. So because we have this, then we can start to create products just like you see here, where we have individual houses of fit and their heat maps and their heat scores or heat ratings, as we're calling them now, are created. So let's talk about some of these. So multi-scale heat maps can be created for individual buildings, at the community, and at city scale. So at the top left, we take the grayscale image and we colorize it from red to blue, and it's scaled from the minimum temperature of that building within the polygon to the maximum temperature of that building. This allows us to visually look at each building and compare them together. Then what we do is we take the average values that we get and we use those, or we take the thermal information and we create what we refer to as a heat score. That heat score's got a lot of secret sauce in it, but the values range from 1 to 10. 1 is low waste heat, 10 is high waste heat. In this case, we color them from green to red. Green meaning that it's more efficient. Red meaning that it's losing more energy. Okay, so we're not using blue anymore. Blue would be cool, but it doesn't really give us an idea about how much energy has been lost. And so now we can take individual houses, we can look at those houses and we can look at the information for the individual houses, and we can then create heat scores that can then be put back onto the individuals as well as onto the community. So what's a heat score? Heat scores are ranked numbers between 10 and 1 from hot to cool. They allow users to meaningfully compare the waste heat of one or more houses shown in a heat map with all other mapped houses in the community and the city. And they can be mapped at the community and city scales as well. And they represent simple, useful heat loss back. It's very simple, but it's very, very unique when you're able to tell from a whole city which portion of your city is wasting more heat. So they can be mapped at the house and community scales, and they represent simple feedback. So what are the kind of people, who cares about this stuff? Who's interested in this kind of thing? Would you be interested in seeing whether heat is leaving your own home or your parents' home? Or do you even care about it? Well, it turns out that a lot of people do care. A home is one of the most valuable investments that any of us will probably ever make in our lifetime. It's worth far more than we can pay off it at one moment. And so we're concerned about how it's doing. And even if you get a high energy efficiency rating on a brand new home, over time, that energy efficiency rating will diminish. In fact, in Canada, the Canada Housing and Mortgage Corporation, the one that provides a lot of loans for mortgages, recognizes that after 5 years, your home is no longer the home that you purchased. It's changed, it's deteriorated, it's squeaky. You've got floorboards and things that might not be working as well. Things are not working as they used to. So your home is changing over time. So who's interested in seeing where the energy is leaving their homes? Homeowners are, renters are, building supervisors, people that want to improve the building efficiency, these folks. Contractors, identifying communities for marketing energy efficiency upgrades. Imagine if you needed to find, if you were a contractor and you wanted to be able to sell products for insulation or new roofing material, how could you tell whether or not roofs needed to be replaced or whether insulation needed to be replaced? Real estate agents are increasingly selling properties that are not just beautiful properties that have marble benches or marble or hardwood floors, but also that are energy efficient, that have solar power, that have passive solar, that have different components that are more green. So which of your homes are more green? Well, the green homes are going to be the ones with the lowest heat score. They're wasting the less heat. And construction companies are interested in verifying their building quality. We were working with one fascinating builder, and we showed him the heat map for 3 of his homes when we were first working on the project. And we took it into him and we said, this is your rooftop. These are the rooftop of your 3 buildings. They're losing energy in these 3 major locations. What are you guys going to do about it? And they basically called us into a meeting. It was over lunchtime. They had about 7 or 8 people in the room, and they started discussing what was really going on. And they had the builders, the roofers, they had the people doing insulation, they had the designers. They wanted to be able to improve their construction of their buildings. They take great pride in their buildings. They create net zero buildings. So these guys were super interested. Imagine if you had to buy a home and you could see the energy that was leaving the rooftops. Would you buy a home that was really, really red? Would you buy a home that looked more blue? And if you're a construction company, you're building, wouldn't you like to be able to boast how well your products are? Not just that they look good and that their energy bills are low, but that you actually have evidence about the energy that is leaving the individual buildings. And interestingly enough, service providers and energy utilities are very, very interested in offering energy efficiency solutions. In fact, they get paid by the government to reduce their energy consumption. So to do that, they need to put programs in place for people to reduce their energy consumption. So here's an example of a product we created with Union Gas. It's had about 1 million clients. It's being bought out by another large energy company called Enbridge. And in Ontario, over 9,700 Ontario houses have applied to have their energy bills lowered by getting rebates to help them improve their energy efficiency. So this was a product that we created for them several years ago. So here's an example. This is the city of Hamilton, Ontario, on the lake. So right away, if you're a city planner, you can see where buildings are more efficient, in this case, wasting less energy, than buildings that have a lot of energy or wasting a lot of energy. And as you might suspect, the older downtown core has pretty high heat loss. But it's also interesting to note that there are some of the newer buildings, including one of my homes, used to have very high heat loss. So what you can do is you can either zoom in on this map, or you can go to the search address and put in your home. As you move in further, closer and closer, you can see that the individual building polygons are shown. You can zoom in and click on an individual house. Then at the top left, you get this Explore My Home button that comes up. You click on that. In here, we talk about what is actually happening. It compares your heat rating with your individual home, your neighborhood, and then the whole city as well. You get a heat map of your specific house. You also get to see again where your home is at that location. In this case, we were asked by the service provider to have people use drop-down menus to put in some information about their homes. Now, why would they do this? Because they're eligible for free energy upgrades. How much do you think the energy upgrades are worth? This company was willing to provide energy efficiency upgrades of $5,000 per house. So if you take a few minutes to put in information about your walls, your heating, your house type, then you can potentially qualify. You can also see what your home looks like in Google Maps, qualify for up to $5,000 in energy rebates. So here's a company that realized it was cheaper to pay tens of thousands of people $5,000 to reduce their energy consumption than it was to spend $2.5 billion to create a new gas-powered energy plant to provide more energy that people are wasting. Can you see how this can work? This can be, not only is the energy company doing good because they're providing rebates to people to improve their home, but when the homeowner gets those rebates, they use less energy, they're more comfortable, they have higher energy security, and they feel good about something. They're wasting less energy. It's like a win-win for everybody. So we've also learned through doing this project and numerous other ones now that customers are about 5 times more likely to take action after seeing their thermal image of their home versus just having a simple mail out about reducing energy consumption, because it's personalized for your individual home. The MyHeat platform is 16 times more engaging than a paper mailouts. Paper mailouts are expensive. If you have 1 million clients and you need to send out 1 million paper bills, and each bill has to be printed, has to be mailed, the envelope, the gas involved, and the delivery. Let's just say a million bills cost you $1 million, which is cheap. And you've got to do this 12 times a year. That's 12 million papered mail outs. Instead, what utility companies are doing are they're saying, if you join our product here provided by MyHeat, we will give you paperless billing instead. So they're saving 12 times a year having to mail out their products. We also provide advanced analytics, which provides customers with insight into where their homes are wasting or losing a lot of energy, and it's mobile friendly. And what's really important for the energy efficiency companies is that you can just click on one-click booking for energy efficiency campaigns. People can just click on one thing and someone can come by and start to do an energy assessment on their home. So having said that, there are still a lot of challenges that we're working on. So research and development that's going on at my research lab at the University of Calgary includes these 5 topics. We're doing heat spot detection. We're working on commercial building asset management, developing smart city platforms. In particular, I'm interested in the machine learning of the thermal infrared rooftop patterns to find out if I see a specific pattern, can I diagnose this as an uninsulated attic hatch, or windows that are not working properly, or uninsulated garage. And ideally, we'd like to be able to fly over the world and create energy efficiency metrics from space without having to go into your individual home. So I'm going to briefly talk about these and then I'll be finished. So heat spots are a very powerful visual diagnostic tool. They represent a ranking of the hottest roof locations. And typically we do 10 to 30 roof locations for commercial buildings or for very large buildings. In this case here, you can see number 1 is right beside number 6. Number 1 is beside number 6. Number 2 is way down here. You would never ever guess that these are the hottest locations. Why are these important? Well, if you have a very large building and your roof is hot, you need to find out where is it the hottest. If you've got limited resources to fix it, what do? You need to triage. So you need to be able to determine where the biggest or the worst locations are first and work on those. As an example, this is a building. It's 14,000 square meters. It's a very, very large building. It's a wave pool. It's a recreation center in the city of Calgary. The city spent $3 million upgrading this building with solar PV cells. Can't say the word. And you can see that the building rooftop looks pretty good. There's a lot of blue, and the yellow lines would be the solar cells that would be still warm in the evening time. But it just so happens that there are some issues with this in some of the hottest locations. The number 1 heat spot is 27.9 degrees, almost 28 degrees above the ambient temperature. So the next hottest location is 15 degrees above ambient temperature. So you could use this heat spot information to define the best place to have a heat recovery system. This is really important in Alberta and in Canada, because I'll give you an example. If it's minus 30 degrees outside and you bring in cold minus 30 air, and then you have to heat it to 21 degrees, you've got to heat it about 51 degrees. That's a lot of energy. But instead, if you could take your cold air and you could pass it over a heat recovery system where hot air leaving your building warms up the cold air. So let's say it's minus 30, it goes over the heat recovery system, and now it brings it up to, let's say, 2 degrees or 1 degree. Now you only have to heat from 1 degree to 21 degrees instead of from minus 30 to 21 degrees. So having a heat recovery system is a really good thing, but you need to know where the heat is leaving. It just so happens that heat is leaving at this location right here, and it's almost 28 degrees above the ambient roof temperature or ambient air temperature. So the city spent a lot of money, but here's an opportunity for them now to be able to use the heat information that's leaving their building and actually use it to heat up their building, to use it as a heat recovery system. So this is an example of the different types of things that we can provide. We're in the process of developing smart city platforms. And to do that, we're creating heat loss mapping systems. Heat loss mapping systems. We're putting in the heat loss metrics. We're putting in heat spots. We're trying to develop energy efficiency mapping. You can incorporate within this energy audits. From here, you could use this to be able to figure out where you're going to do retrofit planning. There are many cities where they will provide a certain amount of resources to fix up some of the older homes in the city. Where are those old homes? We can identify every single building. We can identify all the number 1s, all the way to the number 10s, the hottest cities, the hottest building in the city, the hottest building in your neighborhood. It allows for communities to be compared over time, so you can see if you're creating retrofits, how your city or how your municipality is actually improving over time. And this is engaged in with the monitoring that we do over time. Something that's really fascinating to me are all these different types of geothermal patterns that we're seeing. So we started off with about 5 million different rooftop patterns that we're looking at, and we've colored. And so for all the commercial and municipal buildings, you can use these. And as I was putting this talk together, I thought, oh my goodness, I've shown you the same building twice. It just so happens that these are 2 different buildings that are both owned by the city. These are two different buildings. It's not taken at two different times. Look at the area above it. They're completely different buildings. The city owns both of these. They were probably built using the exact same plan. And as you can see from their heat patterns, many of the same heat loss locations are occurring in both buildings. So the engineering that went into both of these buildings has been duplicated, and the energy that has been wasted is also being duplicated. So if you're a municipal person and you're in charge of paying your power bills for your buildings, you'd like to be able to reduce your energy consumption. But how do you know that your energy, which building do you choose? The one that's using the most energy doesn't necessarily mean it's energy inefficient. You can be using a lot of energy and still have a very efficient building. It could just be a very large building with a lot of things going on it. So here's a way, ideally what we'd like to be able to use are these different patterns to understand what is really happening. This is beyond my expertise, so we would get building and structural engineers, people involved in energy assessments to come and help us as we train our systems to understand what these different patterns might mean. When we first developed the heat project, we were using a Google Street View environment, and we were giving a presentation at a company called Homes on Homes. Homes on Homes has a TV program, and he fixes up homes, and his name is Holmes. And we were showing this online, and we had a big lineup of hundreds of people that actually wanted to see it. And finally, this elderly lady shows up, and she clicks on the location to find her house, and this was her bungalow. And she lived on the right side of the house, and her tenants lived on the other side of the house, and they did not want her to be able to have any energy efficiency upgrades. So she did the energy efficiency upgrades on her side of the house that consisted of putting in new insulation in her ceiling. So as you can see, the insulation on her side of the house is blue, or the heat score, the heat is blue. The minimum temperature is 4.2 degrees. On the other side, it's 15 degrees, almost 4 times more. So this is a beautiful example of where the energy is leaving this house. And this is the kind of thing that shows, in this case, one side was insulated, the other side was not insulated. But for residential buildings, we can use it to identify leaking walls, windows, doors, pipes, vents, light fixtures. Remember, we can see the energy leaving at 5/100ths of 1 degree. So it's very, very sensitive. In many cases, we can locate uninsulated attic hatches. And people go, well, an uninsulated attic hatch? You can lose between 20 and 30% of your entire building's energy through an uninsulated attic hatch. Think about yourself shaving. If you're shaving and you cut your jugular vein, it's only a little nick, but if you don't stop it, that thing's going to make a real mess, and a lot of blood is going to come out. In a similar way, your attic is typically at the top of your roof, the top of your home. Hot air rises. If it's uninsulated, it's essentially an open window that the air will move through. And we can pinpoint uninsulated attic hatches with our technology. You can also ideally quantify the amount and location of insulation and link specific locations and conditions with recommendations for retrofit upgrades. So this is ideally what we want to be able to do, because we have millions of homes. We can't look at them all individually. The training will be based on individuals, but then we'll use that to be able to apply it over at the entire cities. So finally, what we're doing is, my real goal, I have a 5-year research program that's being funded by NSERC, which is Natural Sciences and Engineering Research Council of Canada. It's essentially like your research council, your science research council. And my research is about the remote sensing of urban energy efficiency. So we want to compare building heat loss with consumption to model energy efficiency over time, create and map actual energy efficiency metrics at the house level for entire cities, and evaluate energy efficiency over time from space. So as part of that, something that's really, really great that we've recently done, in 2019, we created a pilot project that was driven by a municipally owned utility in Alberta, and it was sponsored by Natural Resources Canada. And our goal was to evaluate 3 years of consumption data and then compare it for 17,000 homes and compare it with our heat loss metrics that we've created, our heat scores, our heat ratings. That portion was led by an academic team from the University of Carleton and Ottawa. And what they found was each incremental change in our heat rating from 1 to 10 represents a reduction in gas consumption of 3 to 5% and a reduction of electricity consumption of 1 to 1.5%. As you look here on the left-hand side, this is natural gas consumption. The bars at 1 and 10 or 1, 2, and 10 were pretty big. The standard variation here is quite large. It's because there's not a lot of homes in our data set that were really, really bad, and there's not a lot of homes that were really, 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 really good. So we have very limited samples because this data set only had 17,000 houses. However, we are currently working on homes on a data set that have over 60,000 houses and learning to apply this. So what does this really mean? This means that a home with a heat rating of 1 consumes approximately 40% less energy than a building of the same size with a heat rating of 10, which means that we can measure a form of energy efficiency from 4,000 feet in the air. So we can fly over your home, we can we can do all of our normalization, our mosaicing, our geometric fitting, our assessments, creating your heat scores for each individual home that is highly correlated with actual energy consumption. Our next goal is to create actually a measure of energy efficiency. So if energy efficiency is doing more with less, and what we are seeing here is wasted heat, then we have two parts to the equation that we really need. If energy efficiency then is going to be equal to the work that you have done versus the energy that has been wasted, or the energy that has been used to create work versus the energy that has been wasted. And because we have the energy that has been wasted, and we're beginning to get more and more access to energy consumption data for individual homes, we don't know who's in the home, we don't know any personal information, just the consumption at a specific location. Then we can really begin to evaluate energy efficiency. It's not a trivial thing to do because we don't get temperature, we don't get gigajoules from our thermal sensor. The thermal sensor sees temperature. So we have to figure out a way to convert temperature into gigajoules, which is not trivial. And I currently am working with one of the service providers, people who make the sensor that we use, to understand how we can actually do this. So in summary, MyHeat creates maps, metrics at the house level, at the community level, and at city levels, and we can work right now on cities that have populations for over 1 million people. So within a couple of weeks, we can acquire data sets for you, and probably a month and a half to 2 months, have over 1 million homes updated and available for you online, providing that we have the GIS polygons and they work to start with. We've created a web-enabled heat loss platform for smart cities, municipalities, for utilities, for service providers, and for homeowners. At the moment, we have about 9.5 million equivalent a million homes available online, or for a population of 9.5 million homes. We've collected data for over 50 different cities in Canada and the United States. We just started working in the US last year. And we have about 12,000 square kilometers of data collected at between 25 centimeters and 50 centimeters, making us the largest high-resolution thermal airborne data set of an urban region in the planet, to the best of our knowledge. And we're continually acquiring more data and doing more work. So if you're interested to know more about what we're doing, we're actually started a recent project with Google, looking at solar energy loads or potential for rooftops. If you're interested to learn more about MyHeat, I would invite you to come and visit us at myheat.ca. Again, our mantra is energy made visible. And if you're interested in potentially joining my research team is referred to as the Geovation Group. It's a small team, we're growing. We used to have 10 or 12 students. Right now we have 2 due to COVID. They didn't die, they just graduated. New people are not coming in because of COVID. But this year I'm in the process of working with 2 new PhD students that will come into the program. There are a number of different projects. I'm associated with the MyHeat program. I don't work at MyHeat. I'm a chief science officer for MyHeat. MyHeat has operational things that they're doing, and I'm interested in the research and development components. So these are an example of some of the different types of projects. We're doing automatic extraction of polygons, not from the color images, but directly from the thermal image. So this allows us just to be able to get our thermal images and automatically extract rooftops, segment rooftops from them. I'm interested in the diagnostic patterns, trying to understand what's happening, seeing if we can create, this is actually a 2D image, and yet we're able to look at it as if it were a 3-dimensional home. What would happen if we had a 3-dimensional home and we're able to fly over that home or around that home? Look at hotspot stability over time. We also have hyperspectral thermal sensors. It's called the TASI 600 that we use with our TABI 1800. So this is the first hyperspectral thermal sensor. It has 32 bands in the thermal wavelengths. I've got a student working on a project right now to distinguish between different roof material types. In this little image, you can actually see green roofs versus brown roofs, or gray roofs and red roofs. They're actually all the same color to the naked eye, but they're different when we're looking at the thermal energy. And so there's a lot of different things that we're involved in. If you're interested, I would invite you to visit the website. Other than that, I am done. I'm probably over a few minutes, but we're all good. Thank you very much.